Bonjour,
Salut Philippe, ça va?
ça va et toi?
Très bien, bonjour. Je vais essayer à... Ciao Carlo.
Alors,
Ciao, aspetta che apro, eccomi.
Ecco,
Ciao.
ciao. Come va?
Bene, bene, benissimo. Un po' appena sveglio, un po' ancora un po' rincitrullito, ma insomma, spero
Meglio
che
dell'altra volta.
sì, molto meglio che l'altra volta.
Philippe, tu veux qu'on essaye?
oui, je veux bien qu'on essaye. Alors, attends, je vais quand même mettre la
Ok.
vidéo. Voilà, je ne sais pas si vous connaissez mon nouveau look Covid.
Oui,
Non,
toi.
Donc, normalement, donc, il faut partager l'écran. Hein, donc, j'essaye de partager l'écran. Voilà. Non, l'animateur a désactivé le partage d'écran. Donc, il faut que tu réactives le
C'est
partage d'écran.
exactement ça que j'avais fait. Attends, juste une seconde.
Tu parles français, Carlo?
oui,
Ah,
oui, j'enseigne en France, donc j'ai
Ah
fait
oui, d'accord, ok.
presque
Donc,
20 ans à Marseille.
oui.
Bon, français, je ne sais pas si tu l'appelles français, c'est du marseillais, mais quand même.
Oui, oui, je vois, il y a un petit accent coloré, fleuri.
Ah ouais.
Oui. Alors, est-ce que je peux partager l'écran
oui,
maintenant?
je suis en train de voir les options. Je crois que je dois te faire host. Comme ça, tu peux tout faire, si ça va pour toi.
Pardon,
Je dois te faire host organisateur, genre.
Ah oui, d'accord, si tu veux, oui.
Mais, attends. Maria, hai delle pile?
On voit de la fumée qui sort, c'est tout que brûle ou c'est...
Oui,
Non,
c'est
c'est moi qui fume. Je suis désolé, mais mon mouse ne marche pas maintenant. Non? Ah oui, ok. Heureusement on s'est rencontrés un peu plus tôt. Je suis vraiment désolé. Non, sicuro che funziona. Sì. Ah.
Cos'è?
Il mouse.
Ah,
la souris.
Les batteries sont pas chargées. Oh là là. Oui, ça marche. OK. Le seul problème, Philippe, c'est que si je te fais organisateur,
tu dois faire entrer...
tu dois accepter toutes les personnes qui rentrent sur la...
Ah oui, mais toi, on peut être co-organisateur. Il peut y avoir deux.
J'espère oui, mais ça me dit de changer host. Je vais essayer, on verra. OK,
Oui,
maintenant, toi,
vous
tu es
êtes
host,
animateur. Mais est-ce que
animateur.
tu peux encore dire oui?
Non, je crois pas.
Ah
Parce qu'il
bon?
il y avait quelqu'un, il y avait Richard qui voulait rentrer.
Alors, comment je fais pour dire oui?
OK, si tu vas en bas, à côté de Share Screen, il y a
Oui,
participants.
oui.
Si tu tapes sur
Ah oui,
participants,
d'accord, je tape sur admettre.
ouais,
Admettre,
exactement.
admettre, d'accord, j'admets tout le monde.
Oui, je suis vraiment
Mais là, il
désolé.
faut faire attention que si, quand je serai en share screen, je verrai peut-être plus ça. Enfin, je vais essayer. Hein. Donc,
Euh,
j'essaie de faire share screen. On va voir ce que ça donne.
Ne t'inquiète pas pour ça. S'il y a quelqu'un qui ne peut pas rentrer, il va m'écrire un message et je te dirai. OK?
OK.
On ne peut pas permettre à tout le monde de partager l'écran, c'est seulement le...
Moi, je pense que si. Je pense aussi qu'il peut y avoir plus. On le fait souvent, qu'il y a plusieurs co-organisateurs, mais je ne sais plus bien comment on fait.
Oui, on peut, mais en fait, il faisait faire ça au début quand j'avais organisé les meetings. Une fois que c'est organisé, on ne peut pas changer les... Je crois.
D'accord.
C'est
Donc là, je partage, mais vous voyez rien, ce qui est un peu étrange. Ah oui,
d'accord.
ça y est. Vous voyez maintenant?
Oui,
Oui,
parfait.
c'est bon.
Mais il en manque un morceau, non? Est-ce que vous avez les images?
Moi, je vois Deriving Bounds Rule from an Inference.
Oui, oui, d'accord, mais moi, c'est en partie caché par les photos.
Pour nous, c'est parfait.
Pour vous, c'est parfait,
Ouais,
d'accord.
une grande fenêtre et après, moi, je vois une petite fenêtre avec toi à côté.
D'accord. Alors, il faut peut-être que je fasse autre chose, je ne sais pas quoi. J'ai plusieurs façons de faire. Je vais essayer autre chose. Dites-moi. Hop. Alors, je sors de là. Voilà. Et maintenant, j'essaye de faire autre chose qui est ça. Là, c'est pareil ou c'est différent?
C'est pareil.
Là, c'est pareil, mais il y a une petite différence, je pense. Si tu bouges le... Je ne sais pas comment ça s'appelle en français. Ah, ben, non,
La
non.
souris?
Oui, la souris.
Oui.
Non, on voit quand même la bouger dans l'écran.
On voit la souris?
Oui, on voit que ça...
Et là, est-ce que vous... donc, hop. Là, vous voyez page 2, page 3 ou pas?
Oui.
Oui. Alors, 165 pages, ça fait peur, donc je ne voulais pas montrer ça.
Je suis désolé.
Il n'y a pas vraiment 165 pages, mais je vais essayer autrement. Alors, attends, je vais revenir au truc avant, parce que de toute façon, ça ne changeait rien. Et là, je fais ça. Hop. Donc là, pour vous, c'est pareil?
Oui.
Et là, on ne voit plus les... Il y a un petit machin noir. Vous voyez le petit machin noir en bas avec les...
Oui.
Oui. Et je crois que ça va partir tout seul. Ça part tout seul au bout d'un certain temps.
Ça devrait...
Allez. Non, ça ne veut pas partir. Si je fais ça, qu'est-ce que ça fait? Hop. Ben non, c'est ça rate. Non, alors ça, c'est pas ça que je voulais, zut. Toujours des petits problèmes.
Philippe, en même temps, tu peux, s'il te plaît, contrôler s'il y a quelqu'un qui...
Oui, je vais le faire. Mais attends, je voulais régler ce problème-là.
Le diaporama, ça change seul, n'est-ce pas?
Voilà, c'est parti là, c'est bon. Ah non, ça revient.
Tu dois
Là,
avoir plein
c'est ce
écran.
petit truc noir en bas que je voulais enlever, mais il n'a pas l'air de vouloir s'enlever. Bon. Tout à l'heure, il partait tout seul.
Le diaporama, ça change tout seul, non? Les pages, il faut faire plein.
Non, parce que ça dépend si on le met en automatique ou pas, mais là, il n'est pas en automatique, je ne pense pas. C'est moi qui clique. Là. Okay. Bon, essayons. Alors, participants, hop, voilà, admettre. Oh là, il y en a beaucoup. Voilà, j'ai admis tout le monde.
C'est pas possible en effet. Donc là, c'est une autre manière de dire où que je la mette. Où que je la mette, c'est le niveau de moi, j'ai toujours son zéro contre la ça, c'est une autre manière de se convaincre qu'a priori, on a une...
Hi, Philippe.
Hello, how are you?
Fine, you.
Ah, Mauro.
Ciao, Christian. Ciao, Carlo. Ciao a tutti.
Da qualche parte ci sono gli
Hello,
uccelli.
Masanao. You're Masanao Zawa.
Nice to meet you, Masanao.
Nice to meet you.
So I suggest we wait, but there are still 3 people left. Marco, Lori, the other Marco too, maybe. So there is someone who has his microphone on, and there is a kind of background noise. If I might ask to, yeah, that's awesome, thank you. As I suggested the last meeting, if anybody has a question about the last part, I mean, I'm sure we're gonna have time today as well to discuss at the end, and we might even have another meeting to discuss another week. But since I'm guessing we're gonna switch topic a bit, we're gonna move to a slightly different, more technical topic. if someone didn't have time last time to ask questions to Alexia, I would suggest do it now, maybe like 10 minutes. Of course, if nobody has question of if you want to wait, that's fine too. I have some, but if I'm the only one, then as organizer, I'm gonna wait or send an email to Alexia, either of those.
Maybe the first part of my talk is a little bit of a reminder of Alexia's talk. So, which is, and so I can present that just to put things back in mind, and then we can make a stop so that you can awesome. Ask questions to either Alexia or me.
Yeah, because I don't remember what I said last week.
But I will say it in a completely different way.
Fantastic. I will have plenty of questions.
Okay, and last thing, yeah. Again, I'm recording the meeting, so as for last time, if you want, let me know. I guess I'm going to Alexia. I'm going to discuss with Alexia the possibility of uploading the video somewhere. So at a certain point, it will be easier to access them. But in the meantime, if you want the video, let me know. So yeah, let's start.
Now we are 16 participants, so it's as expected, or?
So there is the two of the three I was waiting are came. So the only one, here's the fourth one. The only one still missing is Lori. But since she didn't come last time, to maybe I don't know, she's not gonna join us, or she'll join later. So don't worry about accepting. Philippe, if someone wants to come, he'll let me know and I'll tell you. So don't worry about that now.
Okay.
So yeah, let me just, again, thank you and Alexia for this very nice Two Voices talk. Last week was really exciting, and I'm sure today will be too. And you can go whenever you want. Thank you.
Okay, so let's go. Okay, so can you see it full screen? Because for me, part of it is hidden. Is it okay for you? Everything okay?
Yeah, fine, very well.
And can you see the mouse?
Yeah.
Yeah, okay, perfect. Okay, so well, the title is taken from a recent paper in Foundations of Physics, the last one, 2020. So there is a collection of papers that Alexia sent already, which are all published, basically all these ones, and which are also on archive. And the last one has this title, and I will speak about that. So this is the sketch of the talk. So there will be a first part, which will be more like a reminder of what Alexia said last week, but in my own way. So the meaning is the same, but I will use different words. I will also speak more about Bell's inequalities and EPR and things like that. But basically, obviously, the content is the same, and it's based on this paper in some years ago in Foundations of Physics. And then the new part will be two, which will be to try to put some mathematics formalism over the thing. Okay, so let's go. So this is the first paper I published, actually. The very, very first. I was a student with Alain Aspect in thèse de troisième cycle. So I sort of, as we say in French, je suis tombé dans la marmite quand j'étais petit. And I was interested in Bell's inequalities, Bell's theorem. And okay, so this is 40 years ago about, and so I kept following, obviously, this subject. So a very big event as far as Bell's theorem, etc., is concerned was this achievement in 2015. So it's 34 years after our experiments, where people perform what they call loophole-free Bell test. So the idea is the same. Is this basically you have a source emitting entangled pair of photons, and you make measurement of polarization or of spins. It works also with pair of spin 1/2 particle, for instance. You want the thing to be random, the choice of the measurement to be random, the thing to be space-like separated. You want also to detect all pairs. So this was not achieved in 81, 82, but this has been achieved in 2015. And so Alain Aspect himself concluded that this is closing the door on the Einstein and Bohr quantum debate. And so the conclusion, which is generally admitted now, is that the Bell theorem, and the Bell theorem comes from local realism, and this does not work. This contradicts quantum mechanics, this contradicts experiments, this contradicts everything. So I will not speak really about quantum non-locality. So I want to go back to, let's say, philosophical issues. So what is the motivation of these things? Why are we doing that? Why was Einstein, Podolsky, and Rosen, this is the initial ideas, why did they propose that? So, well, what I tell is that many physicists, like me, will support physical realism. So physical realism is the idea that the purpose of physics is to study entities of the natural world which exist independent from our observations and which obey universal and intelligible rules. So the universe is there. We are human, we are women, men or women. We can understand things. We have a brain, and basically, the physical realism is telling we are able to understand and to manipulate an external reality. So if you like that, you are tempted to say, like Einstein said, that what is real is some sort of certain and reproducible events. It's what Alexia said also. If you can get something again and again, you will be tempted to say it's real. So it's related to this EPR definition. If without in any way disturbing a system, we can predict with certainty value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. So from that, they concluded that quantum mechanics is incomplete. There are missing elements of physical reality. So one can try to, this is what Néel said, try to use local hidden variables as elements of physical reality, but it fails. Okay, so we have to do something with that. This is the situation. So obviously what we can do is to read Bohr, because Niels Bohr immediately in the 35 answered this question, this EPR paper, and he wrote something which is considered very enigmatic. The very condition which defines the possible type of prediction regarding the future behavior of the system constitute an inherent element of the description of any phenomenon to which the term physical reality can be properly attached. So it's considered very obscure, but I will try to clarify it. I think this is quite nice, and actually I agree with that. And so in some sense, what we can try to do is to make all these statements compatible together. So obviously, we cannot guess what Einstein and Bohr would say, but well, we can try to guess something and to sort of get some lesson out of that, because otherwise we just take, okay, Bell's inequality are violated, nature is like that, and that's the end of the story. But this is very frustrating. We want more than that. Okay, so what should we do? Oop, voilà. So we change a little bit following Alexia's last week. If we just take Einstein EPR sentence, and if we add without in any way disturbing the system, neither changing the context, do you know what is the context? You remember? We can predict with certainty the value of a physical quantity. Then there exists an element of physical reality corresponding to this physical quantity. It is called the modality. And so if you sort of mix up a little bit the very condition of Bohr, which is basically not changing the context, because this will change the condition. If you want certainty as required by Einstein, you can be happy with that and consider it's not, well, it's not what they wanted in some sense, but it is what we get now. So if you follow this line, you end up with the idea that the object, the physical object, is a system within a context, as Alexia explained last week again. So there is a physical world, there are the observers, there are systems, quantum systems, but between the system and the observer, there is always this context or apparatus or whatever thing you may like it, but it has to be there, and it is a required conditions for the thing to have a reproducible behavior. So then you end up with this so-called split between system and context. Where is this split? Actually, this split can move. This split is very tricky. It has been discussed with many papers. But what is very characteristic of our point of view is that there are some point of view, like many worlds, for instance, which says that the system gets entangled with the context, entangled with the observer, etc. So the system finally swallows everything. So we absolutely deny that. We just said that this context is sort of a classical interface, which is absolutely needed in order to access the system. So if you sort of accept all this idea, you end up with what Alexia told last last week, and there is a very nice sentence, which was also quoted last week, which is quantum mechanics can explain anything, but not everything. This is from Perez and Zurek in 82, same years as Bell's inequalities. So you understand what it means. If I look at any system, I can explain it. But the big whole, the big universe, I cannot. There is no wave function of the universe, if you want. There is something that quantum mechanics can explain. Any object can be split in little parts, which will have a quantum behavior, atoms, etc. But quantum mechanics, as it is now, does not explain everything. Okay, so one can tell at this point it looks very much like Bohr, but Bohr was sort of like that, but not completely. And so we had something. So we may ask the question, what prevents to have a unique context where all modalities would be defined, which would be the classical situations, as explained also by Alexia last week. So we have seen also that in a given context, the modalities are mutually exclusive. If one is true or realized, the other one are not realized within a context. But now the big thing, which is sort of new things, it's not, many people already told that, as Carlo Rovelli and Anton Zeiliger, and use this idea of quantization. That is, you can impose that the number of mutually exclusive modalities in a context is a property of a quantum system. And it is the same in all contexts. So you can change context, but you will always get the same n number. And this is a very powerful constraint. If you add especially that modalities taken from two different contexts are generally non-exclusive. So it's what we said already last year. There are many more questions than mutually exclusive answers. For a given system, you have n mutually exclusive answers, but by changing your orientation, your spectrum galaxy, you can ask many, many questions, and there are too many questions. And so all the issue is basically combining all these things. So you cannot put them in a single context. You would be back to classical, and this would contradict this principle. And this is what you end up in what we consider as to be the quantum problem. So Alexia explained in detail last week, like contextual quantization implies that one must use probabilities. Otherwise, we would violate against this contextual quantization. And if you go to this framework, probabilities are not related to any ignorance, but to the ontology of the theory, because there is no global context where all modalities can be made mutually exclusive. Again, which would be the case classically, but which is not in quantum mechanics. Okay, and this is the end of my first part. So I can make a little pause because, well, as you see, it's the same ideas as Alexia formulated in a slightly different word, with slightly different words, but the thing is the same. And as I will explain in the following, we want to make quantum mechanics without wave functions in some sense. We will end up with wave functions somewhere, obviously, but for us, the basis of quantum mechanics is quantization, a contextual quantization actually. And then since we are realists, we want certainties, and certainties are modalities, which are properties of a system in a context. So it's sort of combination of many ideas by many people, because all these problems are more than 100 years old. Okay, so, well, you see, there are many, usually very often when people speak about realism, what they have in mind is hidden variables. So we are really realist without hidden variables, but with context. Okay, so I stop a few minutes. Questions?
Maybe
I have a question, Philippe.
Philippe, I don't know if maybe it's not the moment to ask this question, but let me ask it. If you want to discuss it later, we can go back, because I think it's the same question that was discussed with Alexia. Let me just ask you, can you go to the slide context systems modalities, just the one before this one, I think. Mm-hmm. It's all very clear except one detail, which I think is what bothered me, maybe others. At some point talking, you said, well, for instance, the context in one particular situation you can think is apparatus that defines the direction of a spin measurement or something like that. Mm-hmm. And then you say quantum mechanics and explain not everything, but anything, which I understand. And I understand if you say that every time I have a system to describe, I need a context, fine. But the question that I think that everybody has in mind, many people have in mind, is the following. If I take one particular case in which you apply quantum mechanics, in which the quantum particle and the apparatus is a context, I'll forget about that. I want to do another application of quantum mechanics. And I want to describe not everything, but one particular thing, which is the apparatus, the Stern-Gerlach apparatus. So this is what was called context before. Can the object that was called context in that, I shouldn't say in that context, before, be considered a system in a new application of quantum mechanics? Well, if you want, I'm describing something else. I'm not describing the electron anymore. I'm describing the apparatus. And it seems to me that your answer is no, but that's the part I don't understand why you force.
At the very, very end, I will recommend this idea. But an important idea is that the context is unbounded. Once you are in the context, there is no context of the context. There is no super context. It's something, it goes to infinity. And if you, at the very, very end, I will comment that. This is a way to understand the things. That is, a context is not separated from other stuff. It's unbounded. And so once you are in the context, you cannot transform your context in a system. If you start from the system, what you can do is to untangle this system with probes, for instance. So it's as you do QND measurement, for instance. So you can easily grow up your context, your system. So you will have a bigger and bigger system. But what we claim is whatever you do, you will not make sense of this system if you don't have a context around it. A good example is a quantum computer. So let's take a quantum computer.
No, but that's a different answer. That's a different question. So the context is not just the apparatus. It's the apparatus plus the entire world, the entire classical world, in a sense.
Yes, yes.
Okay, okay.
Well, it's actually, yeah, in some sense it does not matter. But if you want it to be the classical world, yes, this is what I say when I say it's unbounded. It's connected to everything else. And so it sort of kills, for instance, the Wigner-Friend argument, because if a friend is a friend, there is no way to turn it back into a system. Maybe you know this Renato-Renner argument, which was sort of a sophisticated version of Wigner's friend argument. We can answer exactly in the same way. That is, you have to decide. That is, a way to answer Renato's argument, for instance, is to say that all he speaks about agents, like cubism, agents. You have agents. But the basic thing is that all agents should agree about who is an agent. Otherwise, you are stuck and you go into crazy things. So an agent has to be at the context level. And since there is a single, the context is classical. So there is a single one. So there is no issue about making superposition at this point. You are beyond that. And so it's sort of a postulate. Now, if you want to give it a formal interpretation, I will do that at the very last slide, actually, but at this point, it's just a postulate. You have moved, there is this famous cut, which makes that at some point, you have moved to the classical world. And once you are in the classical world, it's unbounded. You can go as high as you want. So there is no problem with friends. Friends are already human. So you cannot put them back into superposition. So, okay, it's part. Alexia, do you have any more comment on that? Or?
Yeah, it's the discussion of the classicity of the context that we have discussed also a bit by email, and I guess we would need a few more hours of discussions on this point because there can be a technical answer that Philippe will give ideas of at the end of the talk with the type 2 algebras and stuff to understand why your context behaves classically. But before reaching that point, we can say that a context can always be probed using the same kind of ontological experiment that we did. If you put a context in another context, you can check that the kind of states that you are going to build within this partition is non-contextual in the end. So
you can maybe understand that well if you consider that my career has been the career of an experimentalist. My apparatus is something I can describe in my lab book. So it's not a superposition of things. It is an apparatus. And same for Alexia. And so at some point you have gone to the point where everything you want to build or use is defined at the classical level. You see, I think the quantum computer thing makes sense, because a quantum computer, if you ever build a quantum computer, it will be a very, very quantum system, and a huge quantum system. But there is absolutely no way to make sense of this huge quantum system if there is not around it an even bigger context, because you have to write on it, to read on it, to control it, and everything is done at a classical level. We don't have other ways to act. So even a huge quantum system has to be inside the context, and the larger the quantum system, the more sophisticated the context, but always a context, because this is the way you can do something. Otherwise, you are sort of stuck. This is very Borean, I agree, but well.
I have a question related to this context system boundary as well, but it's a bit different. I'd like to know your personal views, because I understand that you are applying this philosophy, let's say, to quantum mechanics itself, but do you believe that there could exist another theory, which is not quantum mechanics, it's another theory with another math maybe, that could in principle describe this context that within the current formalism that you have, you say, no, this is classical and this cannot be.
No, well, again, it's my last slide, but you can include the context in formalism, but not in the standard QM formalism. You have to use this larger algebra, type 2, type 3 algebra. So there are algebraic techniques which allows you to describe sort of infinite limit in the size of the system. And so so many things are different if you go to these limits. This was understood by von Neumann a long time ago. And so in some sense, so this is called as algebraic quantum mechanics or algebraic quantum field theory. And I think this sort of include what I say. But I try to read many papers on this subject. They are all very, very mathematical, so they are hard to read first. And second, people don't all agree. They have pretty different views on the.
Even for quantum field theory, then this context interpretation would still be present then, which quantum field theory is not quantum mechanics, but it's still a formalism, a theory that this notion of context should be present inside the. It's more general.
With quantum field theory, you have to be especially careful with relativity and things like that. But we think the general framework is okay. That is, so for instance, we are led to say that there is no wave function of the universe because you need, at some point, you need to recover something which is a classical framework. So we have I think I can quote you, Alexia. Alexia like to say, there is a context at the edge of the universe.
Thanks.
If you see what I mean.
Philippe, I had a question about the quantization principle and the way you formulate it. So it seems to me that the crucial assumption here is not just the quantization or the fact that there are discrete there's a discrete number of modalities, but the crucial assumption is that the number is finite.
Yes.
And this is what you use to get the probability.
The number of mutually exclusive modalities is bounded. So I think in Carlo's relational quantum mechanics, there is a similar idea formulated in a different way. You say that information is bounded or something like that. So I don't want to spoil your words, but this idea comes in different approaches. That yes, so you know, mutual exclusiveness is absolutely essential. It's a yes-no principle. That is, a door should be open or closed. So we say that yes, sure.
Yeah, not only mutual exclusiveness, but really the finite number of n.
Yes.
So last week I wasn't there. I missed the first part, but I watched the recording. Thanks to Christian, and I saw that there was a discussion about the terminology, whether we should talk about the quantization or discretization of those modalities. But I think the crucial thing here is the finiteness of the.
And it's not only discretization. We had many discussions with Alexia at the beginning about that. Discretization by itself is not enough. That is, if just a dice or coin tossing is sort of discrete result, but it's not enough.
Must be bounded. Yeah.
You need to have more. It's this idea that you have, for instance, yes/no answers for spin 1/2, but you have yes/no answers along many possible Stern-Gerlach direction. And so then you cannot combine to all these answers, because this would be much more than 2 answers. And the number of answers is always bounded to 2 for a qubit. So this boundary, this combination of discreteness and contextuality, this is what we call it contextual quantization, creates either the problem or the interesting.
The same idea came out independently in Zeilinger and Bruckner. Also in the 90s, they also have it as what they see as the main postulate, the finite.
They talk about elementary systems, I guess, or something like this.
Yeah, but right, but they say that any system is made by a finite number of elementary systems, and each elementary system has a finite number of.
I think they even go back to bits. Yes.
Modalities. They also use the language of information, like I used, and they also say the information is finite, which is.
Yes, is also presenting some other reconstructions of quantum theory or other models that may look like quantum theory.
Okay, so yes, sorry.
Yeah, so given that here it's crucial that it's finite. So do you see any hope to be able to extend the arguments to infinite dimensional systems?
Well, it's finite but unbounded, so it's a little bit ambiguous. So this n can be as large as you want. For instance, as you will see the following, everything, my construction will be based on Gleason's theorem. So Gleason's theorem is basically, it goes from the bottom, but it goes up then. And the question of infinity is really delicate. And also you have to be careful about, yes.
Would you just deny the existence of infinite dimensional systems and just say, okay, it's
no,
just
I
a
don't
very large dimension? Or is that
no, but you have to be very careful about that, because there are different kinds of infinities. Basically, there are countable and uncountable infinities, and they are not the same. Countable infinities, which are the usual infinities in quantum mechanics, which correspond to separable state, to inversion basis. For instance, wave function, you can expand the wave function on Hermite-Gauss basis, which is a discrete infinite basis. And this kind of thing is sort of easy. It's just standard mechanics. There is no real problem with countable infinity for the dimension of the Hilbert space, obviously. So like wave functions. So it's, well, for, separable states, what we use in standard quantum mechanics are these separable states with this discrete basis, infinite discrete basis. They are really close to being finite in some sense.
Can I introduce, perhaps, Cyril, this might clarify a bit. There are 2 different issues here, and I think we shouldn't confuse it. One is the number of degrees of freedom.
Yes.
This is not about the number of degrees of freedom. This is much stronger. I mean, the standard quantum mechanics of a harmonic oscillator does not satisfy this postulate, right? Because the number of modalities is infinite. Yeah. And just go to the energy basis, as you have a discrete number of states. So
it's what I call a countable infinity. Yes.
Right, but I think physically there is so in a sense, we're saying every system is a finite dimensional Hilbert space here. But physically, I think that one way of putting it is that take any system that you want, find whatever you want. Take a finite, think classically, take a finite region of its phase space. Okay, phase space has a volume, it's the Liouville measure, that so any region you can associate a volume. The number of modalities corresponding to that is finite. That's always true. So in other words, if you, that's a basic discreteness. It's independent of anything else, the way I view it physically. And if you want to, if you're an experimental, you can say, turn it, this is not about the context. Any system can very well approximate by a Hilbert space with a finite number of dimensions, and you get a very good description of it. I mean, take your Monich oscillator, take this pendulum, put the cat on the energy at a 10 zillion joule, whatever. That's a perfectly good description of this thing here, and it satisfies its criterion.
So yes, so in terms of, this countable dimension of the Hilbert space, I think is not really a problem. But what is a problem, or what requires a new formalism, is a countable numbers of particles, countable infinite number of particles, or countable infinite number of degrees of freedom. Because then the dimension of the Hilbert space is, let's say qubits, just qubits, it will be 2 power n. So if you get n number of particles, number of qubits going to countable infinity, 2 power n will go to uncountable infinity, and this will basically destroy your Hilbert space. And this is again my last slide. I don't want to tell too much, but there is, what is hidden behind is really, and I'm pretty convinced this is a little bit overlooked, is managing infinities. I think in quantum mechanics we are sort of a little too shaky with infinities. There are many papers which speak about that, but first, these papers are a little bit esoteric. And well, okay, we will come back to that later. Maybe I continue. Are you fine if I go to the next steps?
Can I ask one quick question?
Yes.
So going back, I'm sorry, again to the context system split. I accept that once you get to the concept, it's then concept the whole way back. But what worries me is that there seems to be a tension between the fact that the split between system and context is blurred, and the fundamental distinction you're drawing between system and context. So by blurred, I'm thinking of things like Bell's cloud chamber thought experiment, where it's unclear where you draw the line between your system, quantum system, and your classical measuring device, or in terms of your quantum computing example, whether you treat your lasers doing your measurements as something quantum or something classical, or even you could think about this sort of blurred distinction in terms of like measures of contextuality. So you could have sort of degrees of contextuality in terms of some kind of measure of contextuality. So I'm wondering, do you agree that there is a blur there? And if so, how do you reconcile that with the fundamental distinction you're drawing between system and context?
Well, yeah, so there are two answers. The answer, what I plan to do in this talk is just to postulate, to tell it it's like that. And then what kind, is it possible that admitting that there are systems and context, I can sort of reconstruct the standard quantum formalism. So this is what I plan to do in this talk. Now there is this, the question that you are always asking, and this is what Carlo speaks, called the second question, which is, well, okay, you use a context, but what is a context? Why is it a context? What makes it a context? How do you describe the context? And I will just tell a few words at the end about that, because it is still an open question. It's a complicated question. And my own feeling is that it has to do with managing infinities, physical infinities, mathematical infinities, and so I don't have final answers on that. I can just, so do you agree that we, for the time being, we just admit that what I'm speaking about are in context, and I want to describe their quantum behavior, okay? We can go on that?
Yeah.
Yeah, so let's go on. So, okay, so this you already saw, voilà. So, okay, so you know, sort of reconstruction of quantum formalism is sort of delicate because very often it goes into circle. So it just varies some general ideas. So I speak about induction, deduction, and things like that. So what I call induction is starts from experimental facts or theoretical constraints, etc., and try to explain them as a physicist. So, you know, we know from hundreds of years of physics that you will try to build a mathematical model which describes what you see first. And if it works fine, it will allow you to make predictions. How to choose this mathematical model? So this is a problem of induction. Basically, you guess it. And how to choose it? You take the likeliest and the loveliest. Which is words by a guy named Peter Lipton. Maybe he was speaking about tea, I don't know. He's a British epistemologist. He wrote a big book about, which is called about inference, the idea of inference. It's very subtle, you know, it's you sort of imagine, you have constraints, you manage and blah, blah. And finally, you get something. So for quantum mechanics, for instance, what do? Well, it's how we teach it. You take the Davison-Germain experiment, you have electrons, they are particles, you get fringes, the interference fringes. How do you explain that? So you put waves, but what kind of waves? De Broglie waves, okay? So you need any equations. So you put some dispersion relation, you shake everything, you get Schrödinger's equation, and you have a more or less rebuilt quantum mechanics. So it's a hand-waving induction. And then you have the formalism. And then from the formalism, you go to the next step, which is deduction. Which is basically you use it, and then once you have it, you can make a description, prediction, etc. Compare with experiment, and for QM it works incredibly well. So if you are just stuck in the deduction thing, it's a very famous shut up and calculate. But induction is also interesting. That is, where does it come from? So then you can try to rebuild the theory. So another thing, it's what people call reaxiomatization, which is to enunciate principle from which one gets a mathematical formalism. So this was initiated, for instance, by von Neumann again and Birkhoff using quantum logic. So they try to rebuild quantum mechanics from quantum logic. So many people worked on that. Pyron, for instance, in Geneva, many things. It's not very popular anyway. It's pretty tricky. Physicists does not like to very much this quantum logic business, but it's an example. And there are many other examples. For instance, Giacomo, I think, has published a reaxiomatization of quantum mechanics. So you define axioms, and from this axiom, you sort of rebuild the formalism. In my view, for this to work, you must put a significant mathematical content in your axioms, but why not? Would you agree with what I say, Giacomo?
Sure, you must have precise rules to axiomatize. There is not the freedom of inventing without coherent logic.
Sure, yes. No,
but this is the OPT framework, which is something that everybody forgets. They call GPT. GPT is just the freedom of inventing theory. OPT, there is no freedom. There are rules.
But you need rules, and these rules must, in some sense, go together with mathematics.
Right. Yes. It's category theory.
Yes. So then the third thing, the last thing, which is more the way, I don't really want to do that because maybe first I'm not able to do it. The last one is redo induction. So we want to induce standard quantum mechanics, but not using wave functions, no interferences, nothing like that. So we want sort of quantum mechanics without wave functions. And so we should use something. So what should we use? We should use contextual quantization. So let's start from our contextual quantization and try to rebuild quantum mechanics and see what we get. So you guess obviously that we will get quantum mechanics at the end, but it's a little bit like Alexia told last time. We revert the usual orders. We don't put wave function first and get Schrödinger's equation and blah, blah. We put quantization first, and then we try to rebuild something, and it must be a probability theory also, because we have demonstrated that probabilities are needed. So we want a probability theory suitable for contextual quantization. We go for it? Okay, so let's go for it. So what is the fundamental question we ask to our theory? Well, it is, if we are in a modality in one context, we change context, so we get another measurement. What is the probability to go to the new modality? So it's a very simple question. What is probability to find a system in a modality different from the initial one, Bn in context C, if we start in a modality B prime N in context C prime. So it's a matrix. Basically, you start from here and you go to here, and you can go to any, by definition, to any of the modalities in the new context. So it's an N by N probability matrix. All lines sum to 1, because if you start from here, you must necessarily go to one of these. So it's called the stochastic matrix. All the elements are between 0 and 1, and the sum of all lines is 1. So, okay, this matrix can be anything, but in quantum mechanics, we know what it is. In quantum mechanics, it is well known. It's called the unistochastic matrix. Okay, so blah blah. Doesn't want to appear. Ah, yes. So it's unistochastic. So what is a unistochastic? It's a matrix like that, which is done by taking the square modulus of the coefficient of a unitary matrix. So basically, you take a unitary matrix, you take the square modulus of all coefficients, and it gives you all the probabilities. And you see that all lines sum to 1. This is fine. And also all columns sum to 1. It's not I don't impose that. There is no reason, basically. But okay, this is what you get at the end. So basically, what I would like to show is that this matrix, given my requirement, is not an arbitrary stochastic matrix with just lines summing to 1. It is a unistochastic matrix obtained from a unitary matrix. And so, and obviously, each coefficient is Born's rule, because his coefficient is a square modulus of the scalar product in usual terms between this thing and this state and this state as kets. But I have no kets, I have no...
Philippe, just it's very important because this is, if I understand the core of your theory, this is a special kind of stochastic matrix, or is just a stochastic matrix that is determinist? I'm saying there is it's a mixture of permutation.
It allows permutation, it allows any kind of stuff you want.
Yeah, sure, but this is the general stochastic matrix in the sense that all the vectors sum to up, and it is positive, and all the lines sum, line vectors sum to up. 1, right?
All the lines sum to 1 because I must. The columns don't. I don't enforce that the columns sum to 1.
Ah, okay. So it's substochastic.
It's called stochastic, but it's only line.
Only line.
When you have line and column, it's usually called bistochastic.
Bistochastic. Okay.
So it's not bistochastic.
It's not bistochastic. Okay.
It's only lines which sum to 1. I don't impose that imposing that column sum to 1 is very strong, and I have no reason for doing that. You
okay.
I start for C prime, I go to C, so I must arrive somewhere. So the probability, the lines should sum to 1, but for the columns, well, I have no reason to impose. So it's a stochastic, but not bistochastic matrix. But I want to end up with a unistochastic, and the unistochastic is bistochastic. But you get it for free in some sense. Okay? So this is the question. So now what should I do? I need some mathematics. So I can try to start manipulating my matrix, and I observe some stuff. So for instance, just by this very simple algebra, you can show that the coefficient of your stochastic matrix can be written as a trace of the product of two projectors, Pn and a Pm. Pn being a set of n, so projectors are just n by n matrix. So they are projectors, so the product of 2 gives a projector, and the product of 2 different gives 0. And so since n projectors, orthogonal projector in an n-dimensional space, it means that they sum to identity. So this is fine for the Pn. For the Pm, almost the same, but they are not orthogonal. Okay. So you see, it looks almost like Born's rule, because Born's rule is just a product of 2 projectors. So if I would have a 2 orthogonal set of projectors, I would have a unistochastic matrix. But it's not a unistochastic matrix, and so there is no reason that my Pn are orthogonal. Okay, so I can enforce it. I can say, oh, well, they must be orthogonal, and then I get it, but it's a little bit cheating.
Sorry,
Okay.
just to make sure. So for now, we're talking about projectors onto which kind of space?
It's just projectors in this space, which is
probably
n by n matrix. It's a vector space. Yes. So I don't specify whether it's over C over it's real or complex. So I don't really specify. This is true even if everything is real. Or you can do it, you can define the projectors in different ways. If you make it complex, you have to put basically it's Hermitian. If you want complex number, there should be Hermitian projector. That is P equal P dagger. But it can be true even with real numbers. Yes.
Okay. So you don't assume yet that you have a Hilbert space or
no. Well, it's an Hilbert space. It's a vector space. It's an n by n vector space. So it's just matrices. It's very naive calculation.
Here it's a very experimental approach. We really start from the matrix that we would get in the lab, the probability matrix that we get at the change of context.
You manipulate your matrix. You need your matrix, and you just see. Okay, it's like that. Okay, it makes. There are projectors. It looks a little bit like Born's rule, but it's not Born's rule.
Yeah, so
actually, it's the primitive theory that goes with the primitive ontology that I more or less presented last week. What is the most basic event you can describe? This is a change of context. Here is the matrix. What can be the simplest math that can describe this?
Can I make a comment, Philippe?
Yes.
Here I also want to stress similarity and incompleteness of what I was doing. In my old work in the 90s, I have this matrix defined. Mm-hmm. Exactly the same, defined in the same way. It's a change if I call it P, and I have its properties, and then I notice that the sum must be equal to 1, and so on and so forth, and then I write one possible realization of it is that its entry is a modular square of a unitary matrix, which is what you just said. And I said there should be some principles, some conditions which I'm not able to find that forces P to have this form.
I will tell you the condition on the next slide.
Exactly. And I say I've not been able to find it, and I hope that it should be there. And for me, when I saw your realization and the continuity, I said, wow, that's what I was missing. That was my enthusiasm.
Well, actually, you will see on the next slide. I did not find it. Some other guys found it. Okay, anyway, so the next thing is another decomposition, for instance. So I can also write my matrix, so a stochastic matrix like that. So now I'm happy because I have two sets of orthogonal projectors. The Pn and the Pm are orthogonal projectors. They sum to 1. But I have this R matrix. So this R matrix is a non-negative diagonal matrix with some conditions. And I don't want it. I want R to be identity. If R is identity, again, I'm fine. I get Born's rule. But no, sorry, it's not a unistochastic matrix. So there is no reason for R to be identity. So if R is identity, I'm fine. But R is not identity. Okay. So,
sorry, I just have a question, also related to the previous slide. What I'm not understanding is why, so to make interpretation of this matrix, why do you have the context both in the line and in the column? Because if I'm thinking about a measurement, I have my system, I measure an observable sigma x, let's say, so it should be the knowing part of the probability, so the column, if I'm not wrong. So I don't understand why you also have a line in which you say it's a context. For me, you should have a context either only in the column in a way. I'm struggling to interpret.
Only C and no C prime, yes, okay, because you should not know anything. Yeah, it's a very, very smart remark, and actually it will be used in the following. Okay. But presently, I just say I'm assuming that I start from a context, from a given modality, and I change the context. But you will see in the derivation, what I get, I impose it only on this one. And on this one, it can be, actually, I may not know from where I come, and it still works. You will see that. Okay, so let's go on. So you have this one, it doesn't work. So what is nice also is that, okay, if now I don't do anything, if I don't change context, I can keep my projectors and now everything is fine, but it's sort of trivial. That is, if I don't change the context, the probability of Bm when Bn is a trace of the product of the projector, which is a Kronecker symbol. So it's sort of trivial, but okay, it strongly pushes you towards using projectors.
Okay.
Okay, so
cannot be a Kronecker delta. There is some dimension multiplying the delta.
No, why do you tell that? No,
because these are projectors. The projectors makes a delta projector, and the trace of the projector is not 1.
The trace of the projector.
The trace of the projector is the dimension of the Hilbert space, right? So it's just a dimension missing.
No. A projector in this matrix is just a 1 and 0 everywhere else. So its trace is 1.
So if you project on a d-dimensional Hilbert space, you have 1, 1, 1, 1, 1, 1, 1, 1, 1.
No, Giacomo, this is
it's a single
on one thing. You have just a single one and all the zeros on the diagonal.
All my projectors are rank 1 projectors.
Ah, rank 1. Okay,
Yeah.
thank you.
They are all rank 1 projector, and you see when I make the sum of the projector,
in fact, okay, sorry, I missed that. Thank you very much.
Yes, so sorry, maybe I should have said that. Yes, all these projectors for simplicity are rank 1 projectors, and so when they I sum all of them on an orthogonal set, I get identity. So the trace of identity is n, is a dimension, obviously. And for instance, here you see trace of r squared must be n. So the dimension is there, but all my projectors, all the projectors I code there are rank 1 projector. So with trace 1. And the eigenvalue 0 and 1. Okay? Okay, so, well, Gleason. So this is a trick. So what I would say is that I will use my projectors. So let's make some simple assumption. And it's exactly the remark that I had. For the time being, I ignore from where I come. I just care about where I go, which is a measurement context. And I attribute a set of n mutually orthogonal projector to the n mutually exclusive result in a given context. So these are the results. Okay, so now I must find my coefficient. So the probability to find a given result modality Bn given an initial state. So I just assume it's a function f of Pn, which depends only on this Pn, with a Pn associated with a Bn. Okay, well, why not? And then I assume that the probability are additive for mutually exclusive orthogonal projectors. This is very important. They are orthogonal because it's a decomposition of identity. And so for any set of projector like that, or like that, then the probability must sum to 1. This is just my line sum to 1. Okay? All things looks natural. You are happy with that? Okay, so I got it. Here is Bohr's rule. These are the hypotheses of Gleason's theorem. And then Gleason in 1980, my year of birth, shown that the only solution of this is that f of Pn is trace of rho Pn, where rho is a density matrix. You know what is a density matrix. So if you take the particular case where the density matrix is a projector, f of Pn is the square modulus of the scalar product, which is Bohr's law. So it sounds a little bit like magic, I must say. I must say also that between here and here, you have sort of 20 pages of hard mathematics. I will try to simplify it later, but it's really surprising. That is, basically you have to attribute this projector. You have to make this. So the trick is here, obviously. I will come back to that later. So the next of the, I will try to explain what are the problems with this hypothesis, because they look very simple, but actually they are highly non-trivial, and why they make sense for CSM.
Just another question, if
yes,
possible. So just to fix the idea, so here, because what are the things that you have in addition than just using a matrix in which all lines sum to 1? Because as it's Born law here, some extra thing has been constrained, and I don't remember which ones.
No, all the trick is here. All the trick is that I will tell it in the next. So I will tell it in the next slide.
Okay.
The trick is that the probability only depends on the projector, and does not depend on the context in which the projector is embedded. This is the diagram.
It seems to me that there's
but I will tell it on the next slide. So first, physicists don't like Gleason theorems. So because most reconstruction of quantum mechanics, I don't know about you, Giacomo, but Zurek, Massanes, Cabello, just always start by saying that Gleason theorem is inadequate, which is sort of surprising to me.
That's quite true.
Sorry?
It's true, right? I agree.
No, I don't agree.
That people don't like it.
It is true that they don't like it, but why they don't like it, I don't really know. Anyway, what they tell usually is that Gleason's hypotheses are too strong. And the too strong hypothesis is what I just said. They associate projector with measurement result, and they, the Gleasons, assume that the probability depends only on the projector, but not on the context in which it is embedded. And this is absolutely essential and highly non-trivial. You see, where it says, you see here, if you see that like many projectors, as soon as you have 3 projectors, not 2, but 3, you can fix a projector and change the other one. It's a bit like that. But what I tell is that this probability, this one, for instance, if this B1 is this one, will not depend on B2 and B3. So I can rotate like that as I want. It will not change this probability. And same if I block this one and I rotate like that, it will not change this one. And so this is a very strong hypothesis, which is that the probability is associated with the projector, and it does not depend on the whole context. It depends only on the projector. And so, as I will explain in the following, I can perfectly tell, yes.
So you're basing everything, I mean, if I view the other way around, so start from quantum mechanics, you're basing everything on what's that theorem? Koch and Spencer, the
Cohen-Specker. No, it's a different thing, Cohen-Specker.
No, there's another theorem. The theorem that says that even, you know, the measurement of one variable does depend on the context of the other two.
It is Cohen-Specker, but here it's different. What Philippe is talking about, he's talking about probabilities. But Cohen-Specker is about assigning a truth value of 0 and 1. Cohen-Specker is the derivation of Gleason theorem. But here, Philippe is talking about probability non-contextual.
I will come back to that later.
Okay.
You should not mix up what people call non-contextual assignment of values, which is impossible according to Cohen-Specker theorem, and non-contextual assignment of probabilities.
No, to that theorem. I'm referring to another theorem. How is it called? It's BKS.
BKS, Bell-Cohen-Specker theorem.
Yeah, that one.
Yeah. It's the same. It's the same.
Okay.
Yes, but basically, this Cohen-Specker theorem is a negative result. It tells something that you cannot do. Whereas Gleason is a positive theorem. It gives you a result. But there are strong links. But it's a little bit technical, so I can comment on that later.
So
okay.
Can I just have just to check that I understood correctly? So initially you start with a matrix that just has its line that sum to 1, which is very general, not quantum mechanics, to describe stochastic process, and then you find that that such matrix, the probability can be written as a trace of a projector. It can be written with the use of a trace and some projector, and what the extra assumption you use is that the probability in each column only depend on the projector of this column. Is that it in the end?
Yes, you can tell it this way. This is exactly what is written here. The probability to get a given modality only depends on the projector. So this is a mathematical Gleason hypothesis, and I will give a physical justification. So I come back to this one. So you say it's what we just said basically. So this hypothesis made by Gleason is what is called non-contextual assignment of probabilities. The probability does not depend on the context. And what I will explain in the next slide is that actually this is perfectly fine for us, and this is exactly what we call extra contextuality, but I will explain that in the next slide. Then another big criticism is that the demonstration is too complicated. Well, it's 20 pages, it's tough. It is indeed complicated. It is very beautiful, and I will try to give you some hint of that if I have time. And also, Gleason theorem is really, really difficult, but there is another paper, this one, which gives you a much simpler, it's still difficult, but it's much simpler. They call it elementary proof of Gleason theorem. I like the elementary because, well, okay, it's not that elementary, but still you get a sort of feeling of what is going on, and I will try to explain that. Okay, so the first thing is this. So why do you want to make non-contextual assignment of probabilities? And okay, I just tell it as a reminder. You could try to make non-contextual assignment of values, which is that each modality has a value, but this is not possible in quantum mechanics due to Cohen-Specker theorem. But non-contextual assignment is possible, and actually it works, it makes the job. Okay, so let's try, what is this extra contextuality? So this, the basic idea is that the certainty of a modality can be transferred from one context to another. So I take a sort of a super semantic system, which is to tell that, okay, my quantum system is a photon, and this photon can travel in one of 4 optical fibers. So look at this thing as these optical fibers. So this is my context, basically. Once I have defined my optical fibers, I have a context, and I put a photon in that. And if I have a click, sorry, a click, it tells me the photon is here. So my modality is the photon is here out of these 4 fibers. Okay, so it's a modality in a context, in context 1. Now I can mix up. So it's just a permutation, so it's particularly stupid. I put again the detector, and okay, you just follow, then you know that your photon is here. And then this is more tricky. I put beam splitters, so I mix up the thing. So now the third context is incompatible with the second one due to this mixing here, but still my photon has been followed. So you see, you make click, 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 it's for sure. So I'm sure that if I start here, I get here, despite the fact that the contexts are incompatible. So obviously, physics allows certainty to be carried through context. And this is what we call extra contextuality. So modalities, there are extra contextual modalities just due to what I showed them. So it's very idealized, but I will give another example on the next slide. Maybe, okay. Always. Okay, so extra contextuality is the certainty of a modality in a context can be transferred to another modality in another context corresponding to another physical quantity, another measurement. There are different modalities because they are in different contexts. And I will call extra valence. The modalities connected with certainty between different contexts are said to be extravalent, and it is an equivalence class. Basically, it's reflexive, symmetric, transitive, and we will use that. So this, you can sort of, in a given context, you know that all modalities are mutually exclusive, but in different contexts, you can tell that you have extravalent modalities. Okay, well, why not? So this is very idealized. So I give another example, which is super well known. Also, it's a 2-spin 1/2. So the dimension of the Hilbert space, or the dimension, the number of mutually exclusive modalities is 4. I can measure the spin, the operators of each particle, and also the total spin. So the first context, I consider 3 contexts. So the first context is measuring SZ1, SZ2, the Z component of the 2 spins. So you know spin 1/2 is m equal plus or minus 1/2, and you get the famous 4 states, plus, 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 minus, minus, plus, minus, minus. So this is the first context. You can also measure the total spin. So it's the sum, but the algebraic sum. So you know it takes, it's a first year quantum mechanics, it takes 2 values. So S equals 0, M equals 0, which is this one, and S equal 1 with M equal 1, 0, or minus 1. Okay. So these are new states, which depends on this new context. The third context is Bell set measurement. So I have 4 entangled sets, which are given by these things. So these 4 sets are orthogonal, obviously. These 4 sets are orthogonal, and these 4 sets are orthogonal. And they correspond always to 4 mutually exclusive modalities in different contexts. And these contexts are incompatible because the operators don't commute and blah, blah, as usual. But this thing and the thing are extravalent. If you have plus plus in this context, you are sure to have 1, 1 in this context. So in standard quantum mechanics, you would say, ah, okay, well, sure, they are the same vector. But, well, it's not so obvious because there are modalities and there are modalities in different contexts. So it's sort of retrospective. If I rebuild the thing, I must say they are extravalent. I cannot say yet they are the same vector. They are extravalent, which means that you go for sure from this one to this one. Same thing here, 1 minus 1 is minus minus. And also this one, the famous Cypress for bed state is 1, 0. And this one is even more famous, is the so-called singlet state, psi minus for as a bed state, which is also 0, 0. That is the total spin is 0. So you see again, so this is more physical, but the conclusion is exactly the same. The certainty of a modality in a context can be transferred to another modality in another context, and blah, blah. And these modalities with the same red square are extravalent. Okay? Hello? You are still there?
Yes, yes. It's so it's a. If I know you don't want us to do that, but if given a single vector in Hilbert space that has enough information for computer probability independently from the modalities come from, is that the core of what you're saying?
That is, for instance, if I want to compute a probability, I will associate, forget about, because I'm using standard quantum mechanics notation, but just consider them as physical result. I will obviously associate the same result, the same projector with these two modalities because they are extravalent. And then the probability by construction will not depend on the context because, but I will give more details. But it's based on the idea that, you see, the trouble with Gleason hypothesis was that the probability was depending on the projector and not on the context, which is a little bit strange. Now, what I will tell is that if I associate the projector to an extravalence class, the definition of an extravalent class is that it goes through context. But I will make that more precise maybe on the next slide. So I just repeat a little bit the same thing. So when a system interacts in succession with different contexts, certainty and repeatability can be transferred between modalities. This is called extra contextuality. This defines an equivalent class called extravalence. And then given an initial modality and context, the probability to get another modality in another context keeps the same value as long as the initial and final extravalence class remains the same. So little drawing. So for instance, you have 4 modalities here, which may be in 4 different contexts. These two are extravalent and these two are extravalent. Now, if you want the probability to go from this one to this one, since these two are extravalent, they are connected with certainty, this probability will be the same as this one. And so these are connected also, this probability will be the same. So all this probability, all the dashed arrows will represent the same probabilities because the probability does not depend only on the modality, it depends on the extravalence class, which is sort of its connection. You connect with certainty, connect here with certainty, here with some probabilities, but the connection of certainty does not count some sense in the probability. And so all probability represented by dashed line are equal.
So you're saying this is a theorem, not
yes, you have. It has to be carefully phrased. Yeah, yes. In the FOOP, in the Foundation of Physics paper, we show it as a theorem. Yes.
So what are the assumptions that allow you to derive it?
Just the definitions of the thing.
The definition of the equivalence class of extravalent is enough to get this theorem.
Yes.
Okay.
You may look at it.
Okay, because that seems to be very
weak. It's rather, well, it's not super, there is no special difficulty. You just have to be careful. And I think it's okay. If you have any trouble, please ask.
Okay.
So, well, so the conclusion is that these extravalent modalities embed the idea of non-contextuality of probability assignments. So in some sense, this justifies, again, by induction, this last step is not really a proof. So should I, for instance, I could conclude that the probability depends only on the extravalence class, but it's not exactly that. On the other hand, this is what I will sort of exploit. That is, this sort of allows me to induce the idea that the probability belongs to the, not only belongs, but depends only on the extravalence class. And then I will associate a projector to this extravalence class. So this is what is done here. So we come again based on the hypothesis, the projector, the function. And then we can understand too, this statement too, why the assignment of probabilities is non-contextual. It is because the projector is not associated with a modality, but with an extravalence class of modalities. So maybe I just show that. So how does it differ from standard quantum mechanics? So standard quantum mechanics is that you have the quantum state, which is a psi. You can get a projector on psi. So first, obviously, psi is no more the state of the system because the modality requires both a system and a context. And then the big difference is, so if we may try to mix up a little bit the psi and the modality, but actually the projector or the psi is not associated with the modality. It's associated with an extravalence class. And so it's sort of, in my view, illuminates this second hypothesis. It tells what it makes sense. It makes sense because this PN carries the fact that the modality carries extra contextuality, carries the fact that a modality, the certainty can be transferred between contexts. Then I put everything in the same equivalence class, and I put a projector, and I get this f of Pn, this Pn especially, which depends on the projector, on the modality, but through its equivalence class. So you don't care about the other projectors. Okay, well, so questions?
Yes, to go back to the Cohen-Specker theorem and the link with extra contextuality and the Cohen-Specker theorem.
I don't speak about Cohen-Specker theorem, but
no, you don't speak about it. But since Cohen-Specker is linked with Gleason, I guess there is a link between Cohen-Specker and what you do.
Sure, yes. No, but as I said,
here you say you're talking about. So I'm okay with the fact that you have a contextual assignment of probabilities, but when you talk about certainty, it's not probabilities anymore. It's zero.
Yes, sure.
And
but
this is against Cohen-Specker in some, so it's a little confusing.
Okay. Well, I have slides on that. It's a little bit you need first to look closely at Cohen-Specker, what it tells. So it forbids to attribute values, non-contextual assignment of values.
Yes.
But my non-contextual assignment of probabilities, of certainties are fine. It's allowed, but it's not allowed for all modalities. If it would be a 0 or 1 certainty for all modalities, I would violate Cohen-Specker. So, well, it means that when you have different modalities in different contexts, you may have 0 and 1, and then they will be transferred with certainty, but they cannot be all 0 and 1.
Okay.
I have a slide to show that. Remind me, so you know the famous 4×9 demonstration of Cohen-Specker?
Yes.
The Cabello. So I will show you on this example how it works.
Okay, great. Thanks.
But I cannot do it right now. I can do it later if you want. Okay, so let's. Are there other questions on this thing?
Yes, I had a comment, but maybe on a couple of slides before.
Yes.
There seems to be a non-trivial jump here when you use the Gleason theorem, because you started with projectors, which were built just from the results of your experiment in the lab and where you had probabilities. So that there was no reason a priori to have any complex numbers there.
No, complex numbers they will come later, yes.
But then you're using the Gleason theorem.
It's always true.
Which hold in Hilbert spaces, right?
It may be real in Hilbert spaces, it does not matter. Gleason theorem is valid for both complex and I will come back to that later.
So
but Gleason theorem is valid for both real and complex Hilbert spaces.
Okay, but at some point you want to get the bone rule for the whole complex Hilbert spaces.
Sure, but it will come later. I have a slide on that. It's not an extra slide. I will take some.
Okay, I will wait. Thanks.
I also have a question. I think I'm a little bit confused now when I think again about the matrix. You started the thing at the very beginning. So the column or the context. So it means which observable you're measuring basically, and the line or the probability that you find the state of the system in this or this states associated to an observable. So a thing that I'm not sure to understand is that in a way, like you had to prove that the probability of a given column doesn't depend on the on other contexts. So for example, that the P11, P21 only depend on the projector associated to the first column. So you use that in your thing.
I use that as an hypothesis in Gleason, but I don't claim I prove it. I just justify it with the extra contextuality. I discussed that with a friend already. So this is what you need. You need that the projector, this thing, the function only depends on the projector. So do I prove that this is the case? I would not say I prove it. Obviously, if I assume it, I get Gleason. So this is just mathematics. But do I prove it through extra contextuality? I discussed that with a friend who is good at mathematics, and we agreed that I don't really prove it. I induce it, or I justify it, or whatever you want. I make sense of it, but I don't prove it.
Because in a way, what confuses me is that, so for me, in a way, I don't see how it couldn't be the case. So it means that I maybe misunderstood the point, because if you have different, I don't see how you say you measure a spin sigma x, how it could depend on other possible measurements you could do. That's a thing that I'm very confused.
How could it be otherwise?
Let's say you have a different observable, so different context. You can either measure sigma x or sigma z. How would the probability, the outcome probability of a measurement sigma x would depend on the fact that you could also have measured sigma z, or?
It does not work like that. You cannot, no, you are mixing up things. Mm-hmm. I cannot measure both sigma x and sigma z because they don't commute.
Yes.
So
yes,
here,
I agree.
Yeah. So here you see any of the lines are commuting operators. Mm-hmm. So I can measure both SZ1 and SZ2, or I can measure both S square and SZ.
Ah, okay. Yeah. Okay. So the column, the projector associated to the different column, must be orthogonal, and then it's not obvious that I agree. Then it's not obvious that the result of the first column doesn't depend on the other observable you measure in the other. If they commute, it's not obvious that. Okay, I see. See. Thank you.
Yeah. So you see, obviously, all lines are jointly measurable. They are commuting set of operators. So you can, and they are mutually exclusive, and everything is nice. But on the other hand, the different lines are incompatible measurements. Now, despite the fact that they are incompatible measurement, there are connections that we call this extra contextuality stuff. It's not obvious because you see, I could choose other states and it would not work. It's not
So in a way, what you say is that maybe by measuring S square and SZ here, we could infer some prediction about the probability SZ1 and SZ2, but you say no, it's not the case. It's what happens associated to S square and SZ. The probability are independent on what would happen if I knew the probability SZ1 and SZ2.
In general, yes, except for the special equivalent modalities.
Okay. In some cases, the opposite, right? If I measure S square equal 1 and SZ equal 1, I deduce that SZ1 equal 1 and SZ2 equal 1. That's extra balancing.
Now, I try to repeat. Let's say I start measuring that. SZ1, SZ2, I get plus. So I say, okay, I get plus. Now I measured S squared and SZ. So I say, they are incompatible operators, so I will get random result. In that case, no, I don't get random result. I get 1 for sure.
Exactly.
Which is not obvious because if it was plus minus, for instance, the first one, then I would get just garbage on the other one. It's completely random.
Then I'm puzzled again, but we can continue, and I will think about it in
why are
parallel.
you puzzled?
It's just that for me, as I understood your point, you want you use the fact that the different that what happened in your different columns, so the different projector, the result of the first column doesn't depend on the projector you have in the other column, the column 2 and the column 3, for example. Do you confirm that in the matrix you built initially? So then there is some kind of independence. You shouldn't be able to predict the probability in the first column, knowing, for example, if you were able to know the second column, it means that it wouldn't give you extra information about the first column. Is it somehow the philosophy of the argument you used?
I'm not sure I understand your point.
The way I understood the fact that you want the outcome of the first column to only depend on the projector of the first column, in a way means that if you knew the projector of the second column and the measurement probability associated to the second column, wouldn't give you any clue about the coefficient you put in the first column.
Sorry, I'm lost. I cannot tell whether what you tell is okay or is in agreement with what I tell or not.
Okay.
I hope.
So here, Marco, I think you're talking about different columns, and Philippe is talking about different contexts.
Yeah, but a column is associated to a context.
No.
Because
but you have to be careful also that
for me, each column, as I understood, each column was associated to a given context of measuring.
No, each column, no, it's not a column is not associated with a context. A line is associated with a context. Let's go back.
Column is associated with a modality in a given context.
Okay.
You see, this is here. It's an initial modality. Let's say I start from C prime. You have to be careful. Yeah. The beginning is C prime. I just use this notation for convenience. I start from here and I end up in C because I want to end up in C. So the context is all these possibilities are given a context. Now I don't have other you cannot see extravagance here because I have only a single context. I don't have enough context to show that. What I can tell, yes, if imagine that you have an extravagance, I think it would be much better if I show you the current speaker example because, but I don't want to do that now. I can do that
later. Yeah.
Okay. Okay. So well, so are there other questions on this at this point? So yeah, you have to be careful about what is proven and what is not proven. What is really proven is well, Gleason's theorem. That is, if you assume that, you get that. You get the Bond's rule. But what I do is an induction. So what I want to do is to justify this hypothesis, not to prove them. Otherwise, I would have to make some axiom very. So we did that also in some of the papers. But actually, I think with Alexia, we got convinced that trying to make tricky axioms which are not transparent is not the best way. The best way is more to have a physical argument like extra contextuality. Okay, I can transfer the certainty between contexts. And then from that, I justify some hypothesis, which is what is written here. And given this hypothesis, I'm stuck that I get the result I want. And what is very different from usual quantum mechanics is the idea that a projector is really psi, is really not a state. It is at best associated with an extravalence class. So you call it, well, so you see, you don't want to repeat always the same thing, but the physical thing is a modality which requires a system and a context, and the psi is associated with an extravalence class, which is, it describes the possibility of transferring certainty between contexts with certainty. And then if you admit all these ideas, which are more on the physical side, then you make sense of this hypothesis, and then the mathematics does the job. But the mathematics are highly non-trivial. But I will still, so next step is, this demonstration is too difficult. Well, so I can try to explain. I don't know what I'm doing with the time. How much time do I have?
So I think, honestly, I think that as regards to myself, it would be nice to understand this connection between Gleason theorem and Koch-Specker. So even though we still have only half an hour, I would suggest you do this, you try to give us this explanation. That's my own point of view.
Yeah, but okay. So
if you prefer trying to finish and then come back to
well, I will try to finish and then I go to current speaker. So I will go fast. So what is Gleason theorem? So again, hypothesis, a theorem. So the fact that you can write the probability as trace of rho Pn in the demonstration, it's called F is regular. So if F is regular, if this is true. So this is just convenient, as you will see. So now, how do you demonstrate that? So there are basically two steps. One step is to show that if F is regular in a real three-dimensional Hilbert space, then it is regular in a arbitrary n, real or complex Hilbert space. So this is what mathematicians call a reduction. Basically, you go the other opposite way. If this was true, if this was wrong, the other one would be wrong, and then if the other one is true, then it cannot be true. Okay. But this is tricky. So I will simply admit it. So you have to admit, or you can read this paper, which is really nice, that if F is regular in a real three-dimensional Hilbert space, then it is regular always. That is, this is always true for real complex arbitrary dimension Hilbert space. Now, the real funny thing is to show that F is regular on a real dimension 3 Hilbert space, because this is just three-dimensional geometry. This is what is funny. It all depends on three-dimensional geometry, and then it's a real Hilbert space. It's just ordinary space. It's an Hilbert space, but it's real and it's three-dimensional. So it's just like a standard geometry. So if you show that this is true in such a space, then, and if you believe Gleason or these guys, Cook and company, this is true always. So let's try to show that this. So what you are looking for is a probability function f of u. U is now a three-dimensional vector in R3, so that it's between 0 and 1, because it's a probability, and the sum of the 3f is 1 for any orthogonal basis u, v, w in R3. This is what you want to show. And if you show that, you have everything else. So I will simplify even more. Again, in the general proof, it's not simplified, but I will simply assume that the extreme values 0 and 1 are reached. That is, there is a u, so that f of u is equal to 1, and then the other two are equal to 0. This is just for simplification. You can do the full stuff, but it's just more tricky, more pages, more effort. So now, if the value 1 is reached, I assume, so it's three-dimensional space, it's basically a sphere. I assume that it's reached at point P, some point P, f of P equal 1, and I put it at the pole of my sphere. As a consequence, all f of q for q on the equator are equal to 0. Okay. Now let's take an arbitrary basis u, v, w. Then the quantities, the cosine square of the angle up, are just the squares of the component of the normalized vector p in the basis u, v, w. So they sum to 1 because it's normalized vector. So it's good. This is exactly what I want. So if I take simply h of u equal cosine square of the angle, it is an acceptable function of u, and it's a good one because it's a square modulus of the scalar product between p and u. So you see first that you can find it rather naturally. That is the function that you look for are basically the component of this p, p with a probability 1. This is the initial state in some sense. You start from here. And if you go to this measurement basis, UBW, then the probability to get either U or V or W will simply be the cosine square of this thing. So it is an acceptable function. But the real difficulty is to show that it's a good one. But is it the only one? Gleason shows also, which is highly non-trivial, that it is the only possible one. So let's try to do it. It's very sketchy, but just to give you an idea of how it works. So you see an arbitrary function, f of u, since you are on a sphere, should depend on theta and phi, the latitude and the longitude. So the latitude, you know, like on a sphere, this is the pole, this is the equator. So the latitude is going along this line, and the longitude is going along this side. So you see that this cosine square depends on the latitude because it depends on this angle, but it does not depend on the longitude, which is sort of strange. Why is it so? So you should show that in polar coordinates, f of u depends on the latitude, but not on the longitude. So there is a lemma which was found by Constantin Piron, much after Gleason, that it's basically if you have two vectors in the northern hemisphere, so that h, so these are the cosine square, h of u is larger than h of v, so it just means that u is smaller than v because basically it's just a cosine of the angle. Then one has this thing, so it goes in the same order. Okay, so first you have to show that, and it's not obvious to show. It's okay. So then you make a map. So this is the longitude, and this is the latitude. You have this u. So now what you show is that if f of u depends on the longitude, it will vary. That is, for a given u, a given latitude, it will go between a maximum and a minimum as a function of the longitude. Same thing for another u prime. But due to this thing, if you squeeze the stuff, the upper value here can never go above the lower value here. Otherwise, you will get a contradiction because the maximum of u must always be smaller than the minimum for u prime. So if you go make u go to u prime, that is, you have closer and closer measurement, let's say, this leads to this thing, and this is not possible because this contradicts this inequality. So actually, if you squeeze everything, you do squeeze it, and you end up with large m equals small m, and f does not depend on phi. It's very sketchy, but this is the idea. Now, if you want to look at it, you may look at it, but this is sort of subtle, and basically it's based on geometry and topology of the sphere, and then you end up with the conclusion that f does not depend on phi. Okay, but it's not the end because it does not depend on phi. It can be any function of theta, not necessarily cosine of theta. So then there is, so you want to show now that, so if this is still an acceptable f of u, but you could take any function of the cosine square and it should work also. So why, maybe just a cosine power 4, why not? Okay, so now there is a magical lemma. This is really impressive. I like it. If a function g over 1 is such that you must get the three conditions. G of 0 is equal to 0. If a is smaller than b, then g of a is smaller than g of b. And if a plus b plus c is equal to 1, then the sum of the g's is equal to 1. Okay, these are the three hypotheses. And then you are stuck, g of a is equal to a. Try to show that. So I will not show it, it just shows the intuition. So these are ABC. So these are three numbers which sum to 1. Now I want function of these numbers. So this is the length, A is the length, B is the length, C is the length. So G of A will be the length of this one, G of B will be the same, and this. And you see that this violates this condition because you have A which is smaller than B, the segment A is shorter than the segment B. But here, G of A is larger than G of B. So no, it doesn't work. So this is impossible. Also, you have to respect sort of the order. So if you make a little bit of manipulation, what you see is that the only solution is this one. This is that, okay, you have to go straight and A must be equal to G of A, B of A, etc. So these three conditions basically leave no choice that the argument of the function is equal to this argument. So g of a is equal to a. Okay, you like, it's nice lemma. Now, last step, well, you just take a equals the three cosines. You see it fulfills the hypothesis, and therefore you have that. Can you see it? Do you have a black box on the bottom? Or
yeah, unfortunately we do. Yeah.
Oh, sorry, I don't know how to.
If you read it, I think it's fine. If you can read it.
Yeah, yes. So basically, what you get is that the g of the okay, gone. G of the cosine square is equal to the cosine square. So there is no g. So this is done. Basically, you have shown that not only the cosine square is an acceptable function, but it is the only acceptable function. And so if you go to the final step, so okay, so if it is regular on a 3D real space, it works. Then okay, so we admit it, and so that it is regular on a 3D real line. This is what I sketched. Okay, it's just a basically intuitive thing. If you want all the steps, as I said, they are in the previous paper. So since f is regular on any dimension, we conclude that it is also regular, and that's it. And so this is Reason theorem. So somebody asks, why complex? I will tell that next slide. Give an ID. There are many reasons. So, you know, for the Hilbert space to be complex, but I will give one. But the Reason theorem is valid for real or complex. I just had a little remark because I think it's a wrong thing that I heard many times, especially by Chris Fuchs and company. So people say that, yes, all this requires dim equals 3, you see. So some people tell that Reason theorem does not apply in dim 2. So you have to use other stuff, and this is not nice. And what about qubits? But actually, it is not correct. When you make all the steps of Reason's demonstration, you use complex dimension 2 Hilbert space. What you should not do is to consider only a single qubit. If you have a single qubit, you cannot show anything. And actually, this is well known. Clauser and Bell have shown a long time ago that you can make a classical model of a unique qubit. But as soon as you have 2 qubits, you have a space of dimension 4. And then you have subspace of dimensions 2. And then they obey Reason theorem. So the classical model fails if the qubit is among several qubits. So if you have a qubit which is 1/2, one among 2 qubits, it has to be quantum. Obviously, you have entanglement, Bell's inequalities, and all this stuff. So this is nice. But I think this is really wrong to tell that Reason theorem does not apply in dimension 2. It does apply in dimension 2 under the condition that dimension 2 is a subset of a larger dimension, at least 3. And then it works. And I like that also, because I was, you know, perturbed by this thing, because there is these old papers by John Clauser constructing classical models for qubits. And apparently this is true. So, well, it's very bizarre that a qubit is classical. But actually it is not, as soon as you have 2. And then this is fine. Also, maybe you know, well, I'm going into detail, so I stop here. Okay, maybe one more slide here. So how do you get real quantum mechanics? So you have these projectors, which are 1D projectors, as I said, rank 1 projectors. When you make measurements, you get eigenvalues, AN, and you can reconstruct, as usual, spectral theorem. You can reconstruct operator as some over all possible projectors or eigenvalues of AN, PN. So this is very standard. So this is how you get back the operators, sorry, from the projectors. And the last step is the famous unitary matrices. So since for each context you have a set of orthogonal projectors, then they are connected by unitary matrices, as usual, which may be either orthogonal if it is real, or unitary if it is complex. So possible argument for justifying complex is to tell that if you start from the same from one context, and if you sort of move out, if you change progressively your context, you want to go from the initial P, the initial set of projectors, to any other set of projectors continuously, and including permutation. You want, as I saw, you can permutate your modalities. It doesn't change much, but still you want to do it continuously. And then this requires the matrix to be unitary. It will not work with, it's a, you know that if you have a permutation can have a determinant plus or minus, +1 or -1. And so if you only use orthogonal matrix, you cannot reach all permutation. If you want to reach continuously all permutation, you need complex unitary matrices. And this has to be a group, etc. Okay, so well, this is sort. It's not the only one, but okay, this is sort of a justification for needing. If you want to follow your change of context, then you need complex numbers. Otherwise, it will not work with permutation. Little stop. Questions?
Just a quick comment on this argument. So you introduce a unitary to justify that you have unitaries.
Sorry, you introduce?
Well, here in the argument, you introduce some unitary, the sigma.
Yes.
To somehow justify a posteriori that you were using complex numbers. So you introduce numbers to justify the use of complex numbers.
Yes, because in all in all the previous thing, it might be real. That is what I call unitary real is what is called the orthogonal matrix. It's you consider a real vector space, and if you make a basis change in a real vector space, it's an orthogonal matrix. So you could, so far there was no real argument to decide between complex and real, because Gleason also is valid in both cases. Yes?
I would say something about the real Hilbert space instead of complex. There is one crucial aspect of quantum theory on real Hilbert space, that it doesn't satisfy local discriminability. So, because I don't see here, maybe I'm saying, the talk is very interesting. I would love to have also the transparencies to review. I want to think about. But what I don't see here is explicitly the composition of systems. So, for example, the way in which entanglements comes out. The point is that if you have a real quantum theory, you cannot make a tomography of a joint state, like an entangled state, by local tomography. You need to do a joint tomography. So it doesn't satisfy the local discriminability.
Yes,
when you compose two systems, what is the rule of composition?
Yeah, yes, I ignore that. Well, it's tensor product, but I did not speak about that, and you are perfectly right, Giacomo. Not everything in there.
Because this is very important. It's very important because say the composition of system is a crucial thing of quantum theory. Because otherwise, this is why there was the failure of quantum logic, because Piron never considered the composition of systems and just focused on a single system. So you need to have some rule about composition. This is crucial. So otherwise, you don't have entanglement, which is really the
Sure. I can only agree with Giacomo. So we thought about this tensor products thing. So I have something, but it's not really ready to be discussed. But basically, we do what everybody does at this point. But no, I don't want to comment more. But you are right. And what I fully agree on also is that there are several arguments to justify complex number. So this is one possible argument. I won't claim it's an ultimate one. But in our framework, you see, we don't use the tensor product here. I didn't speak really about tensor product. This argument fits in the current framework.
I have also a little question. There is a result that generalize the Gleason theorem to POVMs. Do you have?
Yes.
Take a look at it.
Sure. No, I know it very well. It's Bush theorem. It's usually called Bush theorem, but I have a big problem with that which is that it assumes additivity of probabilities for non-commuting quantities, for non-commuting operators. And I think there is no physical basis for that. For instance, if you assume that, I can make a one-page demonstration of Born's rule without Gleason's theorem. This was done by, it is in von Neumann book, and I do that to my student. If you assume that for any operators, the average of the sum is the sum of the average, then I demonstrate Born's rule in one page. And I have even that page a few slides away. So I am very reluctant to admitting additivity of probabilities for non-commuting operators. So this is also the trick in Gleason. You admit the sum, the probability sum to 1 for mutually exclusive events. I know no probability theory where you have the additivity rule of probabilities for things which don't commute. Even if you take don't commute for 2 projectors, it's no more a projector. So if you take the sum of 2 projectors, it's not a projector in general if they don't commute. So yes, so I know that, but I don't like it. And also for Bush theorem, yes. Yes.
My question was because here you're only talking about projectors, and so you can have generalized measurements like POVMs. And since here you're using Gleason theorem for projectors, I was wondering if you had looked at the generalization of Gleason to talk about generalized measurements in CSM.
Yes, sure. As I said, but for me, it's not a good proof. For me,
but yeah,
I always POVMs like that. So when I have a POVM, you know that very well, where you extend your space and you go back to orthogonal projectors.
Yeah.
This is my usual way to. I consider that POVMs are just always obtained by tracing some stuff, tracing out stuff, and so. This maybe I'm wrong, but this is the way to get POVM. So rather than tracing, I go one step. I add some degrees of freedom or whatever, go back to orthogonal projector, and then this extension of Gleason to non-commuting operators, I'm really reluctant because I don't. You see, all my thing is based on the fact I want. Adding probabilities is that I add probability of mutually exclusive. If your events are not mutually exclusive, what does that mean to add probabilities? I don't really know. Well, this is okay. This is sort of an answer.
Sorry, I already have 2 questions. One from Mauro and one from Carlo. Unless Mauro already was the same. You already asked. In which case?
Yes, I already did it.
Okay, cool. So Carlo, and if you have questions, you can raise the hand so I can see it. And
very simple. Just since you're in that, I want to know, Philippe, have you looked? Are you familiar? There is a lot of literature on reconstruction, more recent of various kind. There is, of course, Lucien Hardy in Canada. There is I don't know, Alexia Greenbaum in Paris, and recently I found quite interesting. Philippe Heun has a reconstruction theorem. Did you look at this? Are you familiar? Are there?
No. What's the name? Sorry.
Philippe Heun.
No, sorry.
No, I'll just wanted to know whether there is a.
No. Well, I can. Well, I'm sorry, I don't know him, so I don't know the work, so I cannot really comment on that. I will. Please send me an email with the reference.
I'll send you the ones I see more interesting. I'm not capable of seeing where the differences are and where the similarities are. So I just wanted to know if you know.
Okay, so more question. Well, you want to see my last slide? So the next slide is the last slide. Okay, so this is about this algebraic stuff. So what we have obtained sort of is this system. There is a context and there is a cut, and this is an infamous, horrible, atrocious cut. Okay, so the system is type 1, countable basis, unitary equivalence of presentation, superposition. Now I want the context to be unbounded. So if you use algebra formalism, very likely it will not be type 1, it will be type 2, type 3, with uncountable basis, a loss of unitary equivalence. You cannot rotate freely because you have a super selection rule, sectorization, updating, etc. Okay, so, and for me, the cut is when you go there on the right side. If you have ancillas, so if you made typically quantum measurement is made with ancilla, you entangle your system with ancilla. So this is just a bigger system, and it's still quantum, and you still have entanglement and Bell's equalities, etc. Like that. But at some point, you have this cut, and you go on the other side. From an intuitive way for me, of the other side, is sort of it's connectivity. There is no more cut. There is only one. Now, if you look at the yes.
No, can I say one thing? But in order to move to type 2 or type 3, you need the tensor product.
You need tensor product.
Because they were built to make infinite tensor product.
Yes, so you see just below now you see a tensor product appearing.
No, actually here we have one of the maximum experts of this kind of type 2 and type 3, von Neumann algebras in general, with Masanao Ozawa is here.
Professor Ozawa is here?
Yes.
Hi.
Hello, nice to hear you.
I'm sorry for the missing to returning your email. But
no problem with that.
I'll return later. Just a moment. But yeah, type 2 or type 3 can be represented on the separable Hilbert space. So the uncountable basis means something different meaning.
Tricky. Yes. I know. I'm trying to understand these things.
Continuous dimensions. So it's different from the naive.
There are many subtleties. Yes. So it's sort of it's just a slide, just a generic slide. So then, if you have a generic measurement, so what do you do? This is my view to say. You want for your modality, you want a system and a context. So for the system, you can describe it with a projector. Say this is a projector of your system, tensor, all the rest. And this thing is a very ugly thing, which basically tells you that you are in context C1 and that you have measured eigenvalue, which tells you that you are in this state Ci. And all the trick is the tensor product, which allows you to isolate the system. So then you can get unitary evolution of this thing, basically ignoring this thing. And this is what you do in a quantum computer, for instance, without error correction. You want this thing to evolve, decoupled from the environment. But this thing is very ugly because, as I said, you cannot really define boundaries, but basically define your context. And since my context is classical, okay. Now, if you make a measurement, this is where you get the trouble because you will change this thing. And you will change this thing in a way which is coupled to that one. If you put a photon counter, if you get a click, you have avalanche of electrons, awful stuff. So you get this coupling. And so it means that you will lose isolation. So then what will happen? So you should, so in the standard view of you get entanglement between the system and the context. The entanglement gets bigger and bigger and bigger. And then whatever you do, there are many ways to explain that. You end up in something like that, which is a diagonal mixture of new states of the system, tensor, new states of the context. So here you have loss of diagonal elements. So how do you lose them? You can say you lose them by tracing out what you don't want to see, which is a standard way, Zurek type. You can also tell that this thing is too big, so big, this part, that it will sectorize, and then you will change your huge tensor product. The tensor product will become a direct sum, actually. So you will have a sum of unconnected subspaces instead of having a tensor product. And anyway, you will get something like that, where you have new states coupled to unbounded contexts due to sectorization, due to whatever you like, with some probability. Since all these things is probabilities, you are in one of this stuff, you look at the result, and then you get what you want by updating, which is one of these states. And then you are back to the step one. You have a new isolated system with a new modality in context C2. So the coupling is basically controversial. Basically, how do you move from here to here? The updating is more or less not, well, that is, if you admit that quantum mechanics speaks about probability, the updating is sort of obvious. If you want, if you have other views on wave functions, etc., it's not so clear what means updating. If you go to evaluate many worlds, actually, even that does not happen because you have still an analytical state here and you end up, I don't know where. But okay, so this is my view. So of the thing, so you see that this kind of sectorization, that is the fact that the context is unbounded, is important. This is my view, as I said. This is based on what I read on the algebraic stuff. This is based also, there is an old paper by von Neumann, 39, that I like very much, which is called Infinite Direct Product. And it explained that, how you, when you have an infinite system, you have to move from a tensor product, which doesn't mean anything because it becomes just too ugly, non-separable. It's just, you cannot do anything with it, but it naturally switch to a direct sum of separable, still infinite, but separable. And then you are back, you get that with standard notation and you are back on track. But okay, all what I just said is at the exploratory stage. I don't have a finite result. I just say that, well, it fits well with CSM because we are we have this cut, we have this context. What it tells you also is that standard quantum mechanics is clearly not enough. It will not tell that unless you make some. As I said at the beginning, it really depends from where to start and where do you start and where do you want to go. So I try to explain that, but it's not completely finished. Okay, this was the most adventurous slide. That's it. So
thank you. Thank you.
Yeah.
I have to say that, yeah, that's a problem. Let me say, as a spectator, it was pretty great and a lot of very good stuff. As an organizer, I must say that I have to say you made my life very hard because now we don't have time for discussion and question. So my only suggestion is the following. So anyway, the group next week is going to reconvene and we'll discuss about, I wanted to discuss more about this stuff and also the connection with Rovelli interpretation, Carlo interpretation. Also because in the group in March, we read Carlo's paper and we discussed it. So I think it's going to be pretty natural for us to have this discussion and to discuss among us about what your talks, Alexia and Philippe's talk. Of course, everyone is welcome, but I don't want the speakers to feel obliged, nor Carlo, nor anyone else. We are going to reconvene next week and discuss that so that we will ask the question to ourselves and everyone is welcome. So that's the solution I found. And again, so it's late, so I can't have questions today. And thanks again to.
So you want to stop immediately? I can stay more if you want, but
well,
to you.
We can stay more, but again, I feel the duty of the organizer, since everyone. I don't want anyone to miss even though there is the recording. I don't want anyone to feel obliged to stay. We can keep going for, like, let's say 15 minutes if you agree, if there are questions. If everyone...
It's okay because I sort of promised to show this current speaker business, so I can show the current speaker business if you, if you want it.
Again, I would love to stay more, but I don't want, I don't want to reply for everyone, and I don't want people to feel obliged to stay. So if you want, we can stay like 10, 15 minutes more. I would love to hear about the Cauchy speaker too, so that would be a good starting point. But again, next week we could reconvene if you want.
Okay, I'm just.
So Christian,
So
regarding next week,
Mhm.
how do you feel like organizing this? Is that a free discussion
Just free discussion, yeah. So given that we already
nothing to prepare a bit in advance or stuff.
not from you for sure. And
Okay.
again, I would suggest that if you can come so that it would be easier for us to discuss because the authors are there. But the idea is to keep discussing what you know, the main insights that you gave us. So yeah, no talk, no presentation, just free discussion.
Okay.
That was the idea. But of course, there are stuff that we cannot, you know, so easily discuss among us if you're not there. One of them is precisely the connection with the caution spectrum. So again, I don't really know what the best solution is here. Of course, if you tell me that you would be able next week to join for discussion only, that would solve every problem.
For me, so I was looking to my, so I have a conf call that I cannot really miss next Friday between 1 and 3. 13 to 15. So it cannot be.
We can talk about. We can you know, find the right time. That's not something to rush about.
I am happy to participate to anything. I kind thing. I mean, waking up, coming at 8 o'clock for me, it's okay. Like today, earlier is a problem. If at some point, Christian, you wrote to me, if at some point you want me to talk about how I see the relation with the relational quantum mechanics, I'm very happy.
Yes, please. Because I missed, and Philippe missed as well, the first journal club that you had about Carlos' paper. So I would love to have a, basic introduction.
It's a short thing, something like, you know, relational quantum mechanics as a variant of Philippe, Alexia variant.
I would like to focus on this analogy and also on why there are so many analogies, and so what does explain these analogies. That because, as you said last week very correctly, I think I still don't understand how there are so many analogies between your positions, since at the end of the day they're assuming this classicality of the context while you're assuming universality of quantum mechanics. So it's hard for me to understand, to explain the analogies given this analogy. So that's one of the things I wanted to discuss. For the time, again, we can do, if Philippe is fine with this, we can do 3 to 5.
Yeah.
15, 17, 3 p.m., 5 p.m., of course.
But no, I'm not available that slot. Sorry.
Sorry, I thought you said you. Okay, can you tell me when you're available?
No, sorry. 3. No, I messed up. You want to make it 3 to 5? Okay.
Yes, correct.
Yes. No, that's fine for me. Yes. My meeting is 1 to 3, so 3 to 5 is okay.
That's precisely why. Okay, cool. Then that's awesome. Thank you, everyone. And I hope, thanks also to Professor Ozawa for coming. And I would be happy if he can join next week too. Also, because we're going to discuss, I hope, also the very last slide again. So thank you, everyone, and see you next week.
Bye. Thank you very much.
Thanks a lot.
Bye.
Thank you, Philippe. Very nice. Thank you.
Bye.
So okay, so we stop here, or
yeah, Philippe, may I 1 sec? So since you are the host right now, you have to end the meeting, and there is a very tiny probability that the meeting is going to appear on your computer. Probably not. Probably it's going to appear on mine. But just when you end the meeting, please be careful in case like some window pop up saying this is your recorded meeting. If that happens, please save it. But again, it's a very tiny probability. I'm just trying to.
Okay. But another way would be that I give you back the hand.
That's a great idea. That's a very great idea.
But how do we do that?
So if you go to participants and you open the participant slot, which is going to appear on the right, Then you go to my name, Christian Mariani.
And just a moment, I am okay. Participant. Okay, I go to Christian Mariani.
Yeah, and
okay,
you click make host, or I don't know
make
how.
host. Activate. No, this is not what I want to do.
No, that was the mute button.
I lost you. Okay, so
should I don't know.
See you. Bye bye.
Ciao, ciao.
Ciao.
French people.
Bye.
How do you say host?
Yes.
What?
No, but I see you. I see your name, but I cannot make you. I don't. Okay.
Try and click. Try and click with the right button of the mouse. With the right button.
On your name?
Yeah.
On what?
If you click on my name with the right button, it should have some.
Okay. So I found it. Yes, nommé animateur.
Yeah.
Okay. So I put that. Changer d'hôte. Okay. Hôte. Changer d'hôte.
Okay. Now I'm the host.
Okay,
Great.
so
thank you.
Yes.
Okay. Now I can end the meeting.
Okay.
See you next week. Thank you. Bye.
Okay. See you next week. Bye bye.
Bye.